Okay, so you need to start. I mean, you might have to do some of the work that I'm going to explain today on a pen and paper. So if you have that with you, it's going to be useful. So let me go back and start from slide 7, where we had talked about the metabolic flux analysis and the fundamental equation for that. So when we look at the equation for the metabolites, we land up with this equation finally. And there are details for this, which I've not explained, but we can do that if there is a need for it. But the idea is that you get a term which is the dilution term due to the growth of the cell, which is this new term that you see here. And what happens is that there are certain assumptions that you can make. So one of the assumptions that you can make is that there is a very fast turnover of this metabolite. That means that if there is a small perturbation, these metabolites, the fluctuation in the metabolites that you see, they are very transient and you can't observe them. Therefore, this term on the left hand side goes to 0. And the other thing that is also an important thing, which goes with this set of equations, is that in this equation, the right hand side, the concentration of the metabolites is very small, first of all. And then also this specific growth rate is also in the order of 1/10 of an hour. So if I look at the next slide, then what I see here is that there are two things that we can do here. Because of the high turnover rate, we can make the left hand side go to 0. And because this term combined with the specific growth rate becomes a very small term, this value in numerical terms is much smaller than the R term which comes here. The rate of change of the metabolites participation which takes place in the rates of the participation of the metabolites in different reactions, sum total of that. So this term goes to become 0, then you have only this R met term left. And from our previous analysis, we had shown that this was based upon the stoichiometric matrix transposed times the individual rates, individual velocities that you see in each of the reactions of this, so per component. Now, so that was the fundamental equation that is derived for doing this flux analysis. So what happens now is that what was previously a complex set of differential equations, in which if we were to look at the nonlinearities that come with R, this would become very complex. That leads to a situation where we are now left with a set of algebraic equations. And if we make some assumptions which are based upon the structure of the equations, the kinetics of the equations, then we are left with a set of linear equations. And by solving that, we get a very good insight about what is happening in the flux of the pathways. All right. Now, just to explain that this pseudo steady state is valid, so I wanted to show you the values here. So the value that you see here is, for example, the yeast cells, X cerevisiae, the intracellular metabolic pools which are there are of the order of so many micromoles, so 0.05 to 1.1 micromoles per gram dry weight. And the dilution rate is about 0.1 hour inverse. So if you multiply this out, you are looking at a factor of 0.005 to 0.01 micromole per gram dry weight per hour inverse. And the flux in the AMP pathway is about 1.1 millimole normally. The ATP pool is about 8 micromoles per gram dry weight. And the ATP requirement for growth is about 0.1 hour inverse rate at which you need to, at the rate of, requirements at the growth rate of this is about 7 millimole per gram dry weight hour. So those are the values that you would see, and based on this pseudo steady state assumption that we see here, which we come into this equation at this point here, this is definitely a valid equation. So, and what we see is the flux is approximately 10,000 times higher than the dilution term. So you can see the micromoles that we see here. So compared to that, what you find is that this is about 7 millimoles, then you can see that immediately that is in the order of 10,000 times higher. So that makes the pseudo steady state assumption quite valid. Okay. Now, with that as a background, I had gone through this before also, so I'm going to start with this one now. So how do we determine the fluxes? So the way we determine the fluxes is by looking at the set of equations that we have and the set of metabolites that we have. So the number of equations that we have would be J, and the number of metabolites we have would be K. That means these are the number of variables, these are the number of reactions or the equations in which they appear. Therefore, the degree of freedom would be F is equal to J minus K. Now, there are three situations that appear. One is the exactly determined system where F is equal to 0. Then you have the overdetermined systems where F is greater than 0, and then the underdetermined systems where F is less than 0. So each of these cases have their own. The last case, of course, you can't solve, but the other case, unless you have other equations coming in, but these two sets you can easily solve. Now let's look at how this is supposed to solve just theoretically. So what you do is you take this G matrix and you break it up into two parts. And let me see if I can go to this mode here. It helps out. So this is the matrix that we're looking at. Okay. If we break it up in two parts, the first part is the measured components, and the second part is the calculated components. So M is for the subscript is for the measured, and C is for the calculated. So what we're assuming is that part of the variables that are there we can't measure, and part of them we can measure. So this gives you a situation where this GC that you see here, this GC, because of the nature of this equation that is dominating exactly making this exactly system and determined system, this will have a dimension of K times K. That's because there are K variables and there are K such total calculation that you would be able to do. So this GC matrix which is there, this GC matrix would be a square matrix of K times K. Now this Vm that you see here, this Vm is going to be of dimension depending upon what this value of this M is. So the dimension of that in such a way that this overall that you see here, this equation, this can be, so to get this equation here, so this left hand side is gone to 0. So to get this equation, you have to have a transpose inverse pre-multiplied on both sides. And if you switch sides, then you can get this equation out here. This is very clearly seen, right? Now, when you have an overdetermined system, the problem that arises is that this VC is not square. Sorry, this GC is not square. If this GC is not square, then what happens is you get what is called a Moore-Penrose inverse or a pseudo square transpose. Okay, and so what will happen is you'll have to pre-multiply by GC first, and then take this combined structure and then use that to find the inverse on both sides. So is that clear? Or do I have to work it out for you? Yes. Somebody has to say something.
So it's clear.
Yeah. All right.
So
yeah.
Could you just tell us what an exactly determined system and an overdetermined system means?
Exactly determined system means that, you know, if you were to it gives you the number of measurements that are there in such a way that if you were taking those measurements, then you will be able to compute the VC without having to do any other manipulation. So what happens is whenever you have a situation where the number of equation matches the number of metabolites, then you get what is called an exactly determined system. That means you have no degrees of freedom. Okay. So which means that if you were to carry out, that means because the number of variables and number of equations are matching, you would be getting a unique solution for every variable that is there. Okay. Now, whenever you have a situation, so that's what is shown here now. But when you have an overdetermined system, you have excess variables, and you could use that extra information. So excess equations present, so that you have more information than that required to solve the set of equations. So that extra information that is there, that comes from the number of equations that are being defined, you can use that to actually correct for the estimates that you get from this set of equations. So that is another feature that is there. But here what we're doing is we are getting what is called the pseudo inverse. Okay, because GC here in this case would be non-square. So the thing is that you'd have to pre-multiply with a GC, then take the composite of that, then take the transpose of that, and multiply both sides of the equation with that, and then you will get this component that comes up as part of the VM term, and then you can recompute this whole thing out to get the set of equations that you need here. Okay, so it just depends on how you write this out. Okay, now we'll do some examples, and let me go back to this example that is here that we were doing. So what I had said was that we had for this is a heterofermentative metabolism of lactic acid bacteria. Anybody know what is the meaning of heterofermentative? Yes.
And does it mean like more than one?
Loudly.
More than one microorganism is being used for the fermentation.
No, not more than one. No. More than one metabolite is being produced by fermentation. Fermentation means when there is less oxygen. Okay. So if you can see, there's an acetate here at the bottom, and you have an ethanol here at the bottom, right? So that is the reason why you will see
fermentation which have multiple outcomes.
Yeah. But so here we have, so in this case, you have, I mean, you could also consider, in a sense, lactate is something that's being produced here, excess. But format you would not consider because that's really part of the TCA cycle, but lactate would go out. But primarily for this kind of bacteria, lactic acid bacteria, the acetate and the ethanol are considered, and the lactate, acetate, ethanol, and lactate are considered to be the excess things that are being produced. Okay. All right. So now this is the framework that we're going to study. So if this is a very nice problem actually, which is used for illustration. So the first step that you do is you essentially break this up into the three components. Of course, there are four components. One is the macro molecules, but we don't have any macromolecules being defined here in the network. So we get the substrates, the products, and the metabolites, intermediate metabolites. Okay. And if you go back and look at the way the equations are, you would be able to match this with the corresponding thing that I've shown you here. Okay. And but this is the one that is important. This is the GC. Sorry, let me just mark it out. This part is the GC, and this is the V component of it. Okay. Now, what we have to do is we have to convert this into the form of the rates, right? Sorry, this is the So okay. So this if you go back now, I'll show you that equation one more time. Yes. So bring it back here. That is at number 7. Yeah, let me just do it here only. So you can see here that we have these two components here, GM and GC, which will be part of this G. So this GVT is going to 0. You have to convert this now, and to do that, we'll go back here. So these are the, so if you go back to the first equation here, this one here, so that is the R met goes to 0. So the R met is going to give you the V here. So we come back here, and so this is going to be the the V is going to be this, where actually we are writing this as the rates, but this is the individual velocities of for each of the components that are there and which reaction. So this would be the net metabolic thing is there. So you pick up this stoichiometric matrix from here. So you pick up the stoichiometric matrix here, and then you construct this where is that gone? This equation there. Okay, sorry, not this one. 7. Yeah, this is the one. This one. So you construct this one out here. Okay. Now, when you do that, we'll get the matrix. This one is transposed, and then the V terms that are coming here. R is going to be 0 on the left hand side, and then you have the G transpose V coming here. Now, look at the first row, the second row, and the third row here. So the first row is pyruvate, second row is second row is not acetate, it's the lactate. This should be the lactate. I made a mistake here. So there. Actually, that is being referred to as this one here. So this actually should be the this full row is this one. This full row, first row is the pyruvate, and this last row is the NADH. Okay, so that's the balance. So the balances are shown there. Now we break that balance up into these components which are there. Now these components that we see here, this is the V for the pyruvate, lactate, and the formate. And here we have carbon dioxide, acetate, and ethanol. So the second matrix G is non-singular, and that can be inverted. We can see that. So what we're saying is that we can measure pyruvate, lactate, and formate, and we want to calculate carbon dioxide, acetate, and ethanol. So what we do is you do the inverse of that, and you work it out, and then you can see that the rates of carbon dioxide, acetate, and ethanol are obtained in terms of the rates of pyruvate, lactate, and the formates. Okay. So if you look at this equation now here, so we have to determine, of course, when you're doing the inverse, we are supposed to do the determinant. Now, in case we were not measuring the formate, which is shown here, but instead of that we were measuring the acetate, then we find that the determinant goes to 0. And that's because this linear dependency is there, which means that the R3 is dependent upon R1 plus 2 R2, right? So, this essentially will give you, if you look at this R1 plus 2 times R2, then that gives you this one. So this gives the linear dependency. So clearly, this would give you some kind of a situation where you can't evaluate this matrix, right? So you'll have this problem here, and because of that, not always can we say that we can pick up the measurements we want, because some measurements might have dependencies and we have a problem. So you have to be careful about that. So if you're doing an automatic algorithm, then that is something that is a check that has to be done when these measurements are taken into this automatic algorithm. Okay. All right. So far, any questions on this?
Hello.
Yeah.
Sir, in that alternate equation, that matrix equation that you have shown, can you please go to that slide? Yes,
This
sir,
one,
that
14. Yeah.
Yes, sir. Sir, here this matrix into suppose this 0, 0, 0 and P lac and P CO2, and these are all equations, like for metabolic equations.
Which one?
These are single equations. This matrix with this P lac and P CO2 product CO2 and P4. These are all
these are
equations.
products. So yeah, you have to go back to this model here. So now you see these things in the boxes are the products. So 1, 2, 3, 4, 5, right? So you come here 1, 2, 3, 4, 5. So yeah, so I've shown you how to set up the equation in the previous class also actually. So there's a model. Maybe I should have brought that here. Maybe tell me. Go ahead. First, let me hear a question.
Matrix actually, like this values. How matrix that is it?
Oh, so actually, there's one step that is missing here, which is which I had explained in the previous class. So for example, you will have to see from glucose to pyruvate. So glucose is a substrate that is getting consumed. So minus glucose, and you're producing these two plus NADH plus ATP plus pyruvate. Okay, is equal to 0. So that's the first equation. So
that's why half also
minus half glucose for this consumption.
Okay,
and then you'll find that plus NADH plus pyruvate, okay, is coming here, and what is it? NADH, pyruvate, and of course we have the ATP, but we're not considering the ATP balance here because there's only one point that the ATP is coming in and one point that is going out, and so that balances out. So you'll have a redundancy that appears, and you'll have these two equations cancelling out finally. So we get rid of those two. Okay.
Okay.
That is also the reason. It's also the reason why when you have a pair, NADH and NADP or NAD plus pair, no. So in those pairs also you'll have to be careful. ADP and ATP pairs you have to be careful. You can't do for both because one of them means the other. So ATP and ATP are always in equal quantities, and we always assume excess of ATP pool in the system whenever you're doing this kind of calculation. So unless there is a very specific amount of ATP that is being produced and it's not getting balanced and it's an unbalanced set, then you account for that. Otherwise, you don't. Okay, clear?
Yes, sir. Yes, sir. Yes, understood.
So you got that, right? So this is going to be all 0 because none of these products are there, but you get these two products. Similarly, now let's take an example of this. So let's look at this part of the equation. Pyruvate plus this one gives you lactate. That means minus pyruvate minus NADH will give you lactate. Now let's come here. So we look at pyruvate balance. So minus. So the next equation is where's pyruvate? 1 minute. This is the lactate here, no?
Pyruvate in the X pyruvate.
Yeah, so pyruvate is here. So minus pyruvate, but where is lactate here? The lactate will come in. Yeah, this first equation only, right? No, this one. So plus lactate. So the second equation is plus lactate.
Because lactate.
Yeah, lactate is being produced. So plus lactate.
Plus
lactate. So the second row, if you look at minus pyruvate minus NADH, right? So that is going to be equal to 0. So that's what you see here, right? Clear? Yes. Right? So actually what you have to do is from this step, because I showed it in the previous class, I did not show it here now. I mean, in terms of the slides, the same example is done for setting up this equation in the previous lecture, last part of the previous lecture, lecture 6. Okay. So this is already set up there, and you can see how it has been set up there. And from there, if you come here, then we just move from that point to this point, which is nothing but R is equal to, so the rates of these are going to be 0, and the individual components that are contributing to that rate is coming from this set of these equations, individual equations where they are present. Okay. So pyruvate is present in 1, in 2, 3, 4, but not in 5 and 6. Sorry, I made a mistake there. In pyruvate is present in 1 and equation 1 and 3, and not, lactate is being consumed in both 1 and 3. Okay. Yeah. I made a mistake there, but that's what this is. Okay. Clear?
Yes. Yes, sir.
All right. So now what we're doing is we are saying that, let's say, so this part we had said how to separate this out. So if I were to say that pyruvate, lactate, and formate are measured, then I can break this up as VM. So this will be GM. So let me go to this full screen mode. In that case, so this would be GM. This would be VM. This is GC. And that is VC. Okay. And so you can see that this GC, when you take this to the right hand side, this is GC transpose inverse. So this is transpose. And I think normal notation is we also write this as transpose, but I just let me write it as transpose only. Okay. So, so the transpose inverse is here. So this is GC transpose. And so this is the GC transpose inverse, ET, and that is the inverse of that. Okay, and this is GC. No, this is GM, sorry, GMT. Right? Okay, if that is the notation I used, I don't know what notation I used there 2 slides ago. So anyway, so this is transpose. So you take the transpose, then you multiply it out, and then you get this. So all of you know how to do inversion, right? Matrix inversion.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Okay, so let's let's continue. So now we are going to look at the case where we are I don't know if this wherever we okay. That is done. We discussed this also. Okay. Now we're looking at the case where we are looking at an overdetermined system, which means there are more measurements than the number of equations that are there, right? So if you look at what I had shown you earlier, if you remember, where is it gone? So when we are doing this here, so we had 3 over here, right? 3 unknowns, which we wanted to, which we had in this part of the equation, which gave us this breakup 3 and 3. That made it exact, right? Now look at this one here. Sorry, this one. Now we are seeing that there are 4 of these. So now we have a asymmetric breakup here. So we have 3 cross 4, and we have got a 3 cross 2 on this side. So this is going to be difficult now because this is not a inverse. So you'll have to do the more Penrose inverse. So what you do is you first multiply this with its corresponding transpose. Okay. So depending on, I only hope I put all the notations right. Yeah. So okay. So this is the G transpose. So you pre-multiply by the GC on both sides. Then you look at this whole thing together and then make that the transpose inverse. Then multiply on both sides again. And so you will get what is the inverse, which is the more Penrose inverse, which is this one here. And now this one is going to be square. So because of that, then you're able to work out. So this is the square term, as you can see here, this one. And this one remains as it is, which comes from there. And now you are able to determine the result. Okay. So you want to try this out? Just work it out by hand and see if my calculations are correct. I'll give you 2-3 minutes. Yes. Where am I? Can you people just try this out once? It's all worked out here, but I want you to just browse with your pen on this one.
Yes.
Okay.
Just work it out once, so at least you have an idea of what's happening. Try it out and see if, and just verify what I've shown on this slide. Okay. So I'm counting down from just like 3-4 minutes. And Shambar should tell me, yes, he's verified this, 1% at least.
Yes, sir. Calculate.
Okay, so this verifies.
Yes, sir. So the inverse would come out to be half, 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 and 3/2. Like it will be a 2/2
Yeah.
matrix of
Yeah.
half, 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 3/2.
Yeah. Okay. So you can see that, right? So fine. Now there's another method that is also used, and that method is the method of Xi and Lee. Okay. Now just be. So this is a little bit. It is used whenever you have a little more. Whenever the numbers are a little higher and you want to kind of have a little more flexibility in how you choose the variables. Okay. So if you look at the slide, it's very important. Now, what we're doing is we are just using just manipulation in terms of matrix mathematics. So really the bottom equation is the equation that you have. So G transpose T times VC is the one that you want to calculate. So that is the equation that you have. And so that is what you want to work with, right? Now, if you break this V, which is present as VM and VC, then the components that you see here would then be compatible with the GT which is present. Else I could have also written this as GMT and GCT, but I don't do that because then this is a redundant format, because that reduces to the previous form, okay, which is the Moore-Penrose inverse. And the first equation becomes redundant. But to assure that redundancy is not there, what we do is we keep the full form here, GT. Now, the first equation is nothing but VM is equal to VM. I think you can see that. All you're doing is from a vector, you're just multiplying it by a corresponding matrix with identity along the diagonals, and you multiply that by VM, you get the same VM. And this part is 0. So this whole thing is about manipulation, where you write it in this form, and you say that is T times V instead of G times V, GC transpose times V. And now you break this up into an arbitrary fashion, T11, T12, T21, T2, depending upon how you want to break this up as V1 and V2. And notice now on the left hand side, you have a VM, which are the measured components. But V1, V2, it has given you some flexibility in terms of that you don't have to be restricted by the VM on this side also, which was the previous case. When you're doing the Moore-Penrose inverse, if you had a VM on this side, you had to have a VM VC on that side, as you can see in the previous slide, and we had to break it up in a certain fashion. But here, in addition to a VM VC, you also have a V1, V2 kind of breakup that is possible. So not necessarily equal to VM VC. So now the important thing is that this T22 that you have here, that has to be invertible, because you are going to use that as a basis for your manipulation, because V2 that is there has to have as you can see, if I were to use the next equation, which is here, the bottom equation, which is a conversion of this equation into this form. If I wanted to use that equation to compute what is V2, then I would have to make sure that T22 is invertible. So that is something that you have to ensure. Now, the rest is very easy, because if that is invertible, it also means that is square. So in that case, in what you have to do is just take this V2 that is here in terms of this V1 and substitute that into this equation. And what you'll find is that VM is equal to T11 V1 minus T12 times T22 and T21, as it comes here, inverse times T21. That component comes here. And so this is called a TR. And so that is how you get a VM is equal to TR times V1. And so now the calculated and the measured and the ones that you want to calculate are given now. The V1 and V2 can be broken up into a fashion that you can decide later on. And this is for much bigger sets of equations, where this redundancy that is not so obvious in terms of not redundancy, but this breakup restriction that is there for VM and VC, which is not obvious in the smaller sets, would become obvious when you look at the larger sets. So this is how this is done. And so if for example, you also have variance covariance matrix F, then you could do an estimation of this V1 and an improvement of that based on this maximum likelihood estimates. And then this becomes a form where you have this TRs being, are the it's almost like the square multipliers of a matrix, and where you essentially use the variance, covariance, variance information and put it here and then get a better estimate of the result. So that will give you a better estimate, which is a least squares estimate of the result of V1. So you could now use the information that is present in the extra information that is present in the set of equations that is extra, and use that to compute a better estimate of V1, which are the calculated components. Now, one example, I'm showing the same example. In the same example, this is the bottom equation, is the bottom matrix part of the matrix is GC transpose. So this is the GC transpose. But now what I'm doing is I'm superimposing on top of it the I that is there. So VM has got 4 components. So pyruvate, lactate, formate, and ethanol. So you have 4 of this here. So that is a 4x4 matrix. So the I is a 4x4 matrix, and the zeros is a 4x2 matrix. Now, but when I'm dividing this, I'm dividing this as a such that this T22 is invertible. So when I break this up, I have a T11, T12, T21, T22. T11 is a 4x3. This is also a 4x3, but these are 3x3s and 3x3s. So now if I do the same thing, I can see that I'll get a result which is where I have this TR, and if you work it out, you'll get the same result. And that is something you need to verify yourself. That what I showed you in the previous one without the previous, the result that we got in the previous set and this one would be the same. So that is something I need to verify by yourself. Okay. So, but you could, of course, improve the estimate of this. And the result that you get here is based on the pseudo strategy, that is that all the noise is distributed among the fluxes here. So if there is any variation that takes place, it's getting distributed here. So you need to work this out and see what result you get. Okay. All right. I'm not going to do any of the other examples because that is something you can see when you check the slides later on when you're doing your self-study on this. And there are some more examples that you can work out and see. So I've given you a few more examples. So this is another one where this is given. So again, in class, I would have asked you to do this. So I don't know if you are going to do this or not, or would like to do this. Would you like to do this? And then I guide you through this on the result. Or would you like to do it by yourself later? Yes, somebody tell me. So there are 2 more examples here which are worked out.
So I guess we'll do them ourselves once after the class, and if we have any doubts, we can ask them in the next class.
Okay. So please do that, because otherwise, I'm going to assume that this is something that you all understand. So just check this out and come back to me on this. Okay. Okay. Now I'm going to start with. So that is the G matrix anyway. It's quite a big one. You might have to. So you would have. I mean, in some cases, if you see a big enough set of equations that come up, you'll find that you might have to use a matrix operation to come up with the answer. Because here, of course, you've got a much larger matrix here, and the result is not going to be easy for you to just work out by hand. Although we are looking at zeros and ones, so it's going to be difficult. Okay, now let's look at underdetermined systems. In such cases, you have got fewer measurements than the degrees of freedom, and there are an infinite number of solutions, and this is only solvable if you put additional constraints, or you have an optimization criteria which you supply to the problem. And often linear programming methods are used to find a solution, but there are other methods also which you will look at. Okay. So when you're doing an underdetermined system, so what happens here is that you have got, keep in mind, that when you're doing this, you have to ensure that the model has included both the forward and reverse reactions. And the reason why I'm saying this here is because when we are writing out the equation, sometimes we forget that the reverse reaction is most of the time a possibility for metabolic models, unlike chemical reaction models. For biochemical or cellular reactions, you have equations which go both sides, and the conventions are required that if you have a reversible reaction, then you include both sides. So now what you do is, after you've checked that condition, you check what are the constraints that are given. So the constraints that are there is the first thing you already know. This is already there, and of course you also know that the rates, the velocities of the individual components that are there have to be greater than 0. Now, if you want to look for an optimal solution, then you say that you're going to minimize some of the fluxes that are there, subject to certain constraint. And these are the row weights that you can define. There are many ways to do this also, but the idea is that you define the problem. So you'll have to give additional constraints. Sometimes when you are dealing with these flux analysis problems, the constraints come from outside. That means there are certain measurements that are taken at the macroscopic level. For example, carbon dioxide evolution rate or oxygen uptake rate, or measurements of some components outside the medium, but you're doing it outside and then bring it back in. So those components are constraints that can be applied. Or that there are some physical boundaries. For example, new specific growth rate cannot be higher than this, or the yield cannot be greater than this component, or some other components like that. Then you can add those components as constraints here. But you need to set up this problem as an optimal problem, optimization problem rather. Now, a simplistic example is given here, very, very simplistic example. So you have two variables, x and y. And if you look at the equation x2x plus y equal to 4, then there are infinite solutions. Now you give the constraint that x is greater than 0, y is greater than 0, then it is chained to this first quadrant. And if you say the objective function is to maximize 2x plus 3y, then you see that there is only one solution which is possible, because 2x plus 3y equals 12 is maximum at that point. So you have one solution which is viable in this case, right? So that's how this is done. Then you also have application to flux analysis, because linear programming is a formalism that can be used. But you have to keep in mind that all variables are non-negative. So that itself is one basis for giving a constraint. The fluxes have to be positive or negative based on the reversibility of the reaction. That means whether we have both forward and reverse. If their reverse is possible, then the negative, depending on, you can choose a convention. Normally, the convention is that you are saying that something that is produced is positive and something that is being consumed is negative. So based on that, you will have to generate these reversible reactions. And the next thing that you do is to get around the problem of the fluxes forward and reverse, you write them separately and add them up as if they are individual reactions that are present. So that gives you this constant formalism. And so you'll have, in addition to this, you'll have this constraint, and then you'll have the problem being stated as maximize or minimize some component. And then you say that, well, that is subject to these two constraints, and that this is the row vector of weights of individual. You have to realize that you could have a vector of weights depending on which of the components of CSX you wanted to actually maximize. Another way to look at this is that you look at the visualization of this problem, and as you increase the number of dimensions, automatically the level of difficulty changes. But at the same time, you see that you could visualize this as planes that are intersecting if you are in the rectilinear coordinate. So in Euclidean planes, when they're intersecting, you get one point, which is the optimal solution. But if you have manifolds, which means that they're not really planes, but they are surfaces, and then in that case, you might have to look for the local maximum or local minimum, or which may be acceptable, or you have to then drive for getting the global maximum and minimum, because that's often difficult. Sometimes the reason, another reason is that the global maximum or minimum could be in a location that is not permitted by the constraints, and so the local minimum, maximum, and minimum permitted by this constraints is the acceptable solution. Okay, another way to look at this is that you could look at two variables. If you were to just break this up into just a two-dimensional problem, then like I've shown you before, you can have two variables defining the plane, and then the objective function is the one that moves. So as it moves, it picks up what is the value that is the highest or the max optimum, and in this case, this would be the optimum. And you can easily visualize that as this traverses the line where it intersects this point, that would be the optimum solution. So if in 3 dimensions, this one becomes a polytope. So of course, there are some ideas of linear program can go through. So in 3 dimensions, there are these ideas of polytopes which are present. So what you'll see is that in this case, you'll have what is called a normal vector, which comes out of the plane at each of the surfaces. So you have a polytope, which means that I've got multiple surfaces which are Euclidean, and the intersecting of these surfaces are giving you these edges. So the solution would be sometimes it's traversing along these edges to get to the point. That's one way to imagine it. And the other way to imagine this is that if it was a polytope which is irregular surface, but then you could have slices of plane which are there on that irregular surface to give you a solution. Or you can also imagine that you would be traversing along that and looking for the highest value of the objective function as you're traversing along that surface, and the vector would define how you move in that plane, because at every point that you move, you change the parameters, and then you find out if the value has changed, and then based on that, there is an algorithm. There are various algorithms which are there, which tell you how to take the next step, so that you are moving in the right direction. So, any questions so far? Oh, nobody is answering.
No questions currently, sir.
Okay, so in that case, let me stop here. What I'll do is I'll ask. I'll have to give you an example of other problems that you can do in the class. So in the next class, I'm going to give you problems to do in the class, actually, because otherwise it's not going to work out, because I don't see how you would be able to do the hands-on. So maybe I'll share the board with you or something, and then somebody can do it on the board, right?
Sure, sir.
Okay. So for today, shall we conclude here? In that case.
Yes, sir.
Okay.
So one more thing, so regarding the assignment, where do we have to submit it?
Oh, I created on the Moodle. I created a assignment with the same assignment that I'd given as an announcement, actually. So I copied that and put it into the same thing, and I've set it up so that you can submit it there. I've extended it by 1 day, so that because I thought maybe Thursday, because till Thursday you could perhaps do it, since there is an extra day there. So I don't know, Thursday or Friday, because we have an extra class. I think 29th is a class. So what day is 29th? 25th is today.
29th is Saturday.
So that's why I gave it till Friday, so that 29th, I think we have another class on 29th, so we can do it on 29th. And in case we have, so we're going to have 2 classes this week, 2 more classes. So tomorrow's class, I'm going to try. The next class I'm going to try to have is where you will be doing the problems. I'll set up some 1 or 2 more problems which you can do, and I'll have the solutions ready, so that after somebody has done it, somebody has to come to the board and do the problem. So we see that people have understood this. Okay.
Fine, sir.
Yes, sir.
Okay, all right. Bye then.
Thank you, sir.
Thank you, sir.
Yeah,
Okay.
yeah.
Thank
Please
you,
check the
sir.
Okay. Please check the Moodle and make sure that you submit there.
So I had one more question regarding the assignment. So in the first question, like you've asked us to state the advantages or disadvantages of the graphs.
Yeah.
So what exactly are we supposed to mention in that? Like,
Yeah, I had
it's
said
not
no
very
that
clear.
you have sensitivity. You have an issue when the main problem is if you are trying to do data analysis of data that you receive from somebody else. If you're doing work in your own lab and you essentially are able to choose the values correctly, it's fine. Else you will find that it's sensitive to large values of S, right? Or rather small
Right,
values of S. Large,
Oh, right, sir.
depending on the plot. So 1 upon V versus 1 upon S would mean that if you have a small value, which is normally taken in the lab, when you start looking at small concentrations, where really the correct value of the enzyme concentration will be, rather the compute when you're computing this, the correct values will be closer to the larger values, which are easier to measure, whereas the smaller values will have more errors, prone to error. So the error gets magnified when you say 1 upon S. So when you say 1 upon S and you plot the 1 upon S, you'll find that, and if you look at the way I've given you the plots, one I showed you in the class, you'll find that the points that you have as a solution, I mean, for the same interval, 0.0 to interval, you'll find that the values are getting further and further apart when you're plotting them. Whereas that does not happen with one of the plots.
Right, sir.
So obviously, then you're getting equal weightage, and you don't have the sensitivity because you're not having any reciprocals coming in. The actual value is getting plotted and you have no chance of magnifying an error which would be present. Okay, so those things get embedded when you're doing these plots, and if people are not careful, then when you're drawing a straight line regression, the values which are higher, which means so smaller values of S, which are having more error, are going to be dominating the slope. So if you have 1 or 2 data points which are in error, they will dominate the way you're drawing the slope. And that slope will give you an incorrect answer because the slope and the intercept are going to be the ones that would be used to compute the kinetic parameters of the enzyme. Okay. So it's really obvious when you plot it, it will become obvious actually.
Oh, yes, sir.
But make sure that the intervals are the same.
Yes, sir.
Okay, when you're doing the S intervals, don't change those intervals. I made the problem very specifically for that, so that you can see how this changes. Okay, and also docx files, PDFs, and Excel files are the only ones that are permitted right now. So you can upload those files. Okay, other files are not.
Sir, for my submission, I've just attached a link to the spreadsheet in the Word doc itself, so that would work, right?
That is fine. That is fine. As long as I can see, that. If you're not uploading, so for the problems, I've given 3 files maximum that you can upload: 1 for problem 1, 1 for problem 2, and 1 for the Excel sheet. If you're breaking up the problem in this fashion, else one file should be good enough, where you embed everything, and 1 Excel file separately. Okay.
There is no option to upload this file.
Huh?
There is no option to upload any file.
No. I said that you have to upload according to. I set this Moodle up in such a way that when you're going to that Moodle assignment, you should be able to. You have the option of setting up the uploading this. You just check
No, sir.
in case.
I have checked.
Huh? Okay, I will just check after. I will just check after this class. I just set it up from my home.
Yes, so there's a setting where it will only starts accepting submissions from today 7 p.m. So after
not right now. It will be after 7 p.m. today. The reason I did that is because I was not sure if I had not mentioned it in the previous email also. I mean, not email, the announcement, and I not had a chance to talk to you. So I wanted to mention what kind of files you can upload. And if in case you had any doubts, you can ask that. And so everybody's on the same page up to this point. So if you finished the work, you can just submit me. You just have to wait until you can submit. That's all. Okay. I think today 7 p.m. Today evening. Yeah, after that you can submit.
Yes.
Okay. All right. Bye then.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Bye.